Thank you so much for everyone to be here, and also thank you so much to the organizers, especially for the invitation to speak. So what I'm going to be talking about is going to be based on these two papers. This first one with my collaborators, Marius Konser, who is also here. I'll be speaking on Wednesday, and Ken van Tilburg. And then this second, most recent paper with my student at UW, Elliot Matarazzo. So, as everybody here knows, non-perturbative dynamics are really important to the structure and phenomenology of the standard model, and also many of its UV completions. In extensions of the standard model, in particular, spontaneous symmetry breaking is often accompanied by the formation of defects. So this can be magnetic monopoles, cosmic strings, domain walls, vacuum bubbles in some form of first-order phase transition. And there are very many extensions of the standard model, from GATS to axion and QCD axion models to models of baryogenesis, where a variety of these various defects are produced in the early universe. So this talk is going to mostly be centered around magnetic monopoles. So typically, we like to classify the existence of topologically stable defects by looking at the homotopy group of the relevant vacuum manifold. So for instance, as has already been discussed, so pi naught being non-trivial tells us the theory has domain walls, pi 1 being non-trivial tells us about cosmic strings, pi 2 magnetic monopoles, pi 3 instantons, and so on and so forth. And there are various examples of spontaneous symmetry breaking from different groups that lead to these types of defects. Let's quickly look at the standard model. So specifically, the electroweak sector of the standard model, we have SU2 cross U1 broken down to electromagnetism through the expectation value of the Higgs, that is an SU2 doublet. So as a result of the Higgs being an SU2 doublet, the vacuum manifold of the standard model, which we can write in this form, looks like naively a 3-sphere. So we can ask what are the homotopy groups of the 3-sphere, and we learn that the pi naught is trivial, so there are no domain walls in the standard model. Pi 1 is also trivial, pi 2 is also trivial, so there are no monopoles. The first non-trivial group is pi 3. Which tells us that, again, just purely within the fields of the standard model, we don't have walls, strings, or monopoles. There are also no defects in the electroweak sector that are unstable, so neither topologically stable nor unstable. Moreover, spontaneous symmetry breaking that we believe happens at both electroweak and QCD scale temperature in the standard model takes place adiabatically, so without the formation of any vacuum bubbles or any type of extended defects. Which is just to say that any sort of form of experimental evidence of any network of defect and or non-equilibrium dynamics in the early universe will be a very clear sign of physics beyond the standard model.
How have you been Celerons, electric Celeron?
Sorry, how you?
Electric Celeron falls outside of your classification?
That's okay, yeah.
But you wouldn't call that an unstable finite,
it's something that exists at finite temperature. We know how to calculate its effects. It's not the same as a network of defects otherwise, right, in that category, so that's okay. Yeah.
Just a slight, interesting, non-trivial.
Sure.
Okay.
Fair. And of course, I'm excluding SU3, which has also, unstable defects like the QCD flux tube and so on and so forth. Many extensions of the standard model, though, as everyone here knows, do often feature magnetic monopoles. So beyond the point-like Dirac monopole, there are all various forms of grand unified theories that contain magnetic monopoles. Theories with extra dimensions, we can form Kaluza-Klein monopoles, also examples in string theory, and so on. In fact, it is so common that inflation back in the day was in part introduced to get rid of all of the monopoles that were going to be produced in the early universe through the Kibble mechanism. And also so common that this led to Joe Polchinski to point out, to come up with his completeness hypothesis, which was to say that a consistent theory will contain dynamical objects carrying all possible charges consistent with the Dirac quantization condition. So in particular, expect any consistent theory to contain magnetic monopoles. And of course, it's a bit of a lie to say that there are no magnetic monopoles in the standard model. It's true that electromagnetism by itself doesn't contain magnetic monopoles, but the moment I couple electromagnetism to gravity, even minimally, that theory does contain magnetic monopoles. And those are the magnetically charged Reissner-Nordstrom black holes. Okay, so the magnetically charged black hole has a radial magnetic field and a metric that is described by this expression, and this is a solution to the source-free Einstein-Maxwell's equations. Okay, so the moment we couple electromagnetism to gravity, which we have to do at some point, the theory does contain magnetic monopoles.
So why do you need to introduce gravity? Couldn't you say the same words for Dirac monopoles?
I just mean, like, when I say introduce gravity, I really just mean I'm minimally coupling electromagnetism to gravity.
No, I understand, but I'm saying, like, couldn't you say the same words for Dirac monopoles? Those are also singular configurations of electromagnetism.
Not really, because, I mean, so Dirac monopoles, you know, I have to assume there is some form of magnetic charge in my theory. But I'm not assuming anything, I'm just coupling electromagnetism to gravity.
Still, there is a magnetic charge.
Yeah, you're assuming it.
Yeah, but it doesn't count because I wrote some current on the right-hand side of Maxwell's equations, right? The equations I'm solving here, this. And this is a solution to this equation. I didn't have to write anything on the right-hand side. You can rewrite this if you want and make it look like there's a current on the right-hand side.
Of the horizon, right?
Sorry?
Because you're only solving it outside of the horizon if you are going to try to think of the solution at the singularity.
I mean, I'm not addressing what is the origin of the singularity, just like we don't do that when we talk about source or black holes in GR, and that's fair.
I mean, the magnetic field there is the same as that of a monopole. Anyway.
As that of a point monopole, and the same is true for an electrically charged black hole, by the way, right? And you agree that, so this is true. The only difference here is whether, you know, this is a magnetic or an electric field, but in both cases, charged black holes are solutions to the source-free Einstein-Maxwell's equations.
Yeah, I agree. I'm just saying that you don't need to say this. You don't need to include gravity. You can already. Anyway, yeah, it's fine.
Well, there's going to be a crucial difference that we'll see later in the talk, which is I'm going to be mostly talking about Euclidean monopoles, for which there is no longer a singularity if this is a black hole, and that is important. Okay.
I think also in SU2, if you take just electroweak theory coupled to gravity.
Absolutely, there is a two-fold. Well,
there are magnetic black holes which don't have this singularity here.
Okay.
Yeah.
Of course, you know, monopoles are also interesting for the point of view of generalized symmetries. Their existence could break explicitly the U1 magnetic one-front symmetry of electromagnetism. Also, they are expected to play an important role in determining certain selection rules for non-invertible symmetry and so on and so forth. So the bottom line is that both from the point of view of phenomenology and also more formal theory, understanding the effect of these type of defects, such as magnetic monopoles on the low energy EFT is obviously a very interesting question. So this talk, as I said, is going to be focused on monopoles, but more specifically on the connection between monopoles and what I'm going to call Abelian instantons. Okay, so the talk will have two parts. I will first discuss Abelian instantons in quantum field theory, and then I'll move on to discuss these objects in the context of a theory of gravity. Okay, so I'll start there. First, let me remind you why the concept of Abelian instantons might be interesting at all. So very naively, if I'm looking at the standard model for the first time and I realize there are 3 gate factors, I would say, well, how many theta terms I can write down in the standard model, and very naively I will write one for hypercharge, one for SU2, and another one for QCD. Then I will realize, as we do, that the SU2 theta term can actually is unphysical, and it can be redefined to 0 by performing rotations on the quarks and leptons. That's a feature of the field content of the standard model. And then we also say that the U1 theta term is unphysical because there are no Abelian instantons. There are no field configurations of U1 gauge fields where the integral of f which f is not 0. So if I were to say that, so what we typically say is that the QCD theta term is the only physical theta term of the standard model, and similarly also, as we know, very, very small. So the existence of Abelian instantons would instead turn the theta term of electromagnetism, or hypercharge if you prefer, into a physical parameter of the standard model. And we do know situations where the theta term of electromagnetism is physical, and that is in the presence of magnetic monopoles, right? So we know that in the presence of magnetic monopoles, if we write down a theta term, here is for the Atouf-Polyakov monopole, but at low energy you can think of it as a theta term for electromagnetism. If we write something like this down, our monopole or our dion will acquire an electric charge that is now proportional to theta. Okay, so something that previously was purely a monopole now becomes a dion. Something that was a dion will become a monopole when theta is 2 pi, and so on and so forth. So the spectrum of dions mixes in the presence of this theta term. The mass of the monopole, or the mass of the dion more generally, also acquires some theta dependence. So we summarize this through what we call the Witten effect, which indeed means that the electromagnetic vacuum angle does become physical in the presence of dynamical magnetic monopoles. And so this is interesting for a number of reasons, one of which was pointed out in this paper by Matt Rees and his collaborators, which is that, so in particular, the QCD axion and other types of axions will typically couple to electromagnetism at low energies through a term of this form. Okay, and in fact, this is one of the most used couplings to look for axion and, in general, axion-like particles. So the idea, the observation made in this paper was that if I have a coupling like this, okay, through the Witten effect, magnetic monopoles will now become dions with, in particular, theta-dependent masses. As a result of that, these dions will generate non-perturbatively a theta-dependent contribution to the vacuum energy density. So if you want, you can think of quantum effects where you are pair producing and reannihilating pairs of these dions, okay? And so if theta is a dynamical field like an axion, this suggests that there is an additional contribution to the axion potential in any theory that features magnetic monopoles. So what these results suggest in particular is that in the presence of monopoles, it should be possible to find field configurations of purely abelian gauge fields such that the integral of this quantity f wedge f is no longer 0. Okay. So how is that possible? So just like for the existence of monopoles, having non-zero instanton number requires that there is enough topology in the theory somehow. So typically, Yeah, so we know that it's possible for non-abelian gauge groups, right, where we classify those instantons by the third homotopy group of whatever non-abelian group we have. It is also possible if the space-time itself is topologically non-trivial. So if instead of doing physics in R4, we lived in a 4 torus, then we can have some field configuration of abelian gauge fields where electric flux is wrapped around one of the torus, and magnetic flux is wrapped around the second torus, and then this will lead to a non-zero f wedge f. A third way that shares some commonalities with these two, but is also in some ways different, which is what we talk about in this paper, is the possibility of having abelian instantons that are supported by closed monopole warlines. And this is what I'm going to describe. Now. Okay, so to explain this, let me first do a very lightning review of the Dirac monopole. So when we introduce the Dirac monopole, we think about just a point-like magnetic charge, sitting at the origin. This is the field strength. If we integrate the field strength around some two spheres surrounding this point, it will tell us the units of magnetic charge carried by this monopole. And we know that it is possible to write this field strength as the exterior derivative of some gauge field, locally but not globally, crucially, right? So we can choose some gauge field, but it will feature some singularity. In this example, for instance, our Dirac string is lying along the C+ axis. we can try to do some form of, we can try to remove the string, but at best, what we can do is just move its location. So we can choose some other gauge field, where now the Dirac string is sitting along the minus z-axis. So it is possible to define a gauge field by patches, and that allows us to describe, again, a gauge field everywhere, so long as at the intersection of the two regions, these two guys are related by a gauge transformation, okay, which is the case in this example. So again, this allows us to define a gauge field that is well-defined and non-singular everywhere, except in this case at the origin, which is where the monopole sits. Okay, so really a Dirac monopole is not defined on R3, but rather R3 with a point removed. So what happens now? I'm going to now consider monopole world lines. In everything is going to be in Euclidean space. So let me start with my point-like Dirac monopole. I put it here sitting along the z-axis. So x4, if you want, is the Euclidean time direction. And I'm choosing some gauge where the Dirac string is along the z+ axis. So as this Dirac monopole travels along some world line, the Dirac string is going to trace some two-dimensional string wall sheet that is called the Dirac sheet. If I consider a closed world line, then in this particular gauge, I will have some Dirac string that is basically this infinite two-dimensional surface in the x3, x4 plane. And just like with the Dirac monopole, I can always define my gauge field by using different charts, such that the gauge field itself is non-singular, except in this case at the location of the monopole world line, which would be this circle. Okay, so these two configurations where the Dirac string lives either sort of outside or inside of this loop are related by a gauge transformation where the two patches overlap. And so again, this allows us to define a gauge theory, not quite on R4, but rather R4 after we excise a loop where the monopole lives. Okay.
I'm sorry. This loop is some field configuration in Euclidean space or something else.
Yes, some configuration in Euclidean space.
So can one write it explicitly? This configuration.
I will get to it. Yeah. For now, first I just want to motivate why this thing exists at all, and then yeah. Okay, so the crucial observation now is that R4, after we excise a loop, is a topologically non-trivial manifold that has, if you want, two boundaries. One would be the boundary at the spatial infinity that we always talk about, so some S3 at the spatial infinity of four-dimensional space, but also now an internal boundary, which is this S1 cross S2. So S1 is the monopole world line, and S2 is some infinitesimal 2S sphere that surrounds the monopole at every point around the loop. Okay. So by definition, the integral of f around this two-dimensional 2S sphere just gives me the magnetic charge of the monopole. And my claim is that if on top of this the gauge field itself has a non-zero, non-trivial winding along this S1, then the integral of f with f will be not zero. Okay? So yeah, so both, a monopole at every point in the loop and a gauge field that winds around this monopole world line, and then you can show by explicit calculation using some convenient coordinates that the integral of f with f factors out into the product of these two windings. Okay. And the minimal instanton and anti-instanton will correspond to +1 and -1 product of these two integers.
Maybe this is not the right place to ask this question, but I'll ask it anyway. So you keep saying instanton, but instanton is a solution of an equation. It's not just a configuration with non-trivial Chern classes.
So I'm using the term instanton here very liberally to define a field configuration where the integral of f with f is not 0. If you prefer me to use a different name, that's fine. But that's what I'm referring it.
And it's a configuration in R4
In
or
R4.
in R4 factorized?
Sure. Yeah, in R4 in this case minus. I mean, it will be in R4. So the fact that you have to excise the loop, right, is just a reflection that the monopole you are considering is a Dirac monopole. In any UV completion, you don't have a singularity at the center of your monopole.
But it's a configuration in R4, isn't it?
Correct.
Not in your Roche some R4 factorized by S1, so I'm confused.
Well, when you include the monopole loop, the theory is only really well defined in R4 minus S1. Just like a Dirac monopole sitting at the origin is really only well defined in R3 minus a point. That doesn't stop you from considering the Dirac monopole.
Okay.
And of course, in some UV completion, you don't have to excite any point because everything will be smooth at the singularity.
There is some singularity on this S1, right? As far as I understood you now.
There is what?
There is some singularity. A singularity.
Yeah, because I'm dealing with Dirac monopoles.
Okay,
Yeah.
so that's configuration which has singularity on S1 in R4, and so that's what you call monopole loop, right?
Right.
Okay.
Can someone get me a glass of water? Awesome. Yes, so I'm using the term instanton just to refer to field configurations where f with f is not 0.
Also, preventing holonomy being integer quantized is a special property in the condition.
So this doesn't indeed. So you probably noticed from my previous slide that while I know this Chern number has to be quantized, I didn't say here that n had to be quantized. Right. However, I do need to demand that f with f is quantized, which restricts this type of windings to only quantized n.
You know it, right? So
You know it from f with f, but you didn't know it at this stage.
okay.
So I'm confused about that answer. So is that the equation that you wrote on the next slide?
Yeah. Thank you.
Is that equation true even if A is not quantized?
Yes.
So f wedge f in R4 minus S1 is not quantized?
So it looks like there are only certain field configurations where f wedge f will be quantized. And I think, when it comes to summing things over the path integral, you would restrict yourself to only including those field configurations where it is quantized.
Why would we do that restriction? If we just imagine having a loop in this monopole, wouldn't we just integrate over all possible values of the connection consistent with that singularity?
I think that is an interesting question. I mean, I think, we do know that for consistency, the integral of f have to be quantized, even at the level of a Dirac monopole, right?
The integral of f over any, compact smooth 2 manifold, yeah, fine.
Yeah.
But here you have the integral of f over something non-compact, you have singularities,
I agree it's not clear that the same theorems that force f wedge f to be normally quantized would apply in this case. Of course, if you're thinking about this monopole eventually being UV completed into something smooth, then some non-abelian theory effectively, then this thing will end up being quantized. But yeah, I mean, in general, nothing forces you for it to be quantized. I think in sensible UV completions we know of, it will be. But purely from the 4D sort of this analysis, it's not forced to be, I would say.
Sorry, don't you want
It's not going to be very important, but
autonomy of the gauge field to be quantized for some definition of what you call U1?
this for sure. But I don't think anything forces me to have this guy be quantized.
That should be U1 phase.
Yeah.
Holonomy should be U1 phase.
Yeah, so, I suspect, again, when you finally UV complete your monopole with any smooth configuration, it will come out to be this way, I suppose. But it's not something you see, I think, purely from the 4D point of view, or the Dirac monopole point of view.
Yeah, another question. So if this holonomy of A should shift if you do a large gate transformation, right? So how do you define this n? Because if I do a gauge transformation, I can shift n by 1.
But if you exponentiate
No,
the level
this
Wilson
is
line,
supposed-
is,
Yeah,
Yeah.
the exponential, yes, but it's not exponentiated, no?
Well, I mean, you should think of it as being exponentiated, just like this.
Okay. Because the integral of f is gauge invariant even if you don't exponentiate it.
If you exponentiate it and then n is integer, then that's 1, right?
Yeah, so you're
Right.
saying that the Wilson line is trivial. Okay, it has to be trivial.
But yeah, nothing in principle like forces this to be quantized in this way. It's not going to be very important, but. And I think that's just the fact that there are some things that you cannot really see just from for the Dirac monopole. I suspect. So yeah, the important thing is that the integral of f with f turns out to be the product of these two windings. Okay. So I would say that what I'm calling Abelian instantons are Euclidean loops of magnetic monopoles, except with a twist, meaning that the gauge field has to further wind around the monopole worldline. So now coming back to your question about whether this is a solution to some equations of motion, the answer is not in this case where all I have is electromagnetism. Two things to say about that. The fact that something is not a solution to the equations of motion doesn't preclude the fact that that configuration still has to go into the path integral, so it will contribute in some way. It difficults the semi-classical expansion we like to use to evaluate that path integral, which is why we're going to discuss gravity later on. But it's still useful to think about what type of sources you would have to add in order to source this type of field configuration. So obviously, first without winding of the gauge field, a Euclidean monopole loop is a solution to Maxwell's equations in the presence of some magnetic current that is localized around this S1. Okay, so you would be sort of like putting in by hand some form of magnetic current, just like you would do for the Dirac monopole. Sourcing the winding of the gauge field around this monopole worldline also requires some form of current on the right-hand side of Maxwell's equations, some form of electric current. Okay, which I've written in this way. So U and B here. So I'm using some coordinates where, as you see here, R4 is covered by two pairs of radial coordinates, U and V, and two angles, phi and tau. Okay, so there has to be some current that you can show is a function of these two radial coordinates, and you can show that, unlike the monopole current, this effective electric charge has to be smooth. Otherwise, your winding of A along this worldline would not be finite, and in fact, you can deduce purely from the 4D analysis that this charge has to be localized around the worldline as 1 over r being the distance to the worldline. Okay, so the magnetic charge is delta function localized on this defect, but the Euclidean analog of this electric charge is somewhat like smeared on top of the magnetic charge. I'm not going to talk about it here, but in our paper, and also Marius will say more about this later, this type of effective electric charge that is somewhat a smear on top of the monopole is precisely what you see when you go to the SU2 version of this, which is the Atouf-Polyakov monopole, rather the Julius Z dion, which is the dion version of the Atouf-Polyakov monopole. So you can also look at what this field configuration looks like far away, which is entirely within the regime of the effective theory. So you can do a multiple expansion of the components of your gauge field, and you find some expression that looks like this. Okay, if you look at it closely, and you remember your quantum field theory, these two terms look precisely like. So the first term up here in blue looks precisely like in this particular choice, one of the components of the field strength of what we call the BPST instantons in non-Abelian gauge theory. What I've got here in green is the corresponding component, but for the anti-instanton. Okay, so if you have a theory like SU2, that is spontaneously broken to U1, where you would have Atouf-Polyakov monopoles. If you look at the instanton field configurations that exist in that theory far away, they are precisely of this form. Okay.
Can you remind us what is little q?
Little q is this. So I didn't say what it is. So M is the magnetic charge of the monopole. Little q is some form of electric dipole coefficient that comes from integrating your electric charge density in some appropriate manner. And so what you can show is that the self-dual field configurations that would actually correspond to instanton charge 1 or -1 are the cases where where these are integers and they are equal to minus plus the magnetic charge of the monopole.
But is that some nice equation for an abelian gauge theory? Therefore, setting Q, setting this self-dual or anti-self-dual condition? Like, could we have guessed that equation a priori?
This, no. So this is the most general configuration that exists. Q doesn't even have to be an integer, or there's no constraint that forces it to be an integer. If I want to focus on self-dual configurations, just for comparison with the usual instantons that we are familiar with, then that would only happen for certain values of Q that are integer. I don't want to dwell too much on this because it's not going to be super important for later, but I'm also happy to talk more about it later. I just think this is, again, a reflection of the fact that there are certain things that are just not forced on us by purely the 4D U1 theory.
Can I ask one? Maybe
Yes.
this is quick to answer. So tau describes the monopole world line.
Sorry. Yes.
And then you introduce another compact direction phi.
Well, I mean, so, I'm choosing coordinates in R4, right, which are like,
Sure, but
and I'm choosing to put this monopole on the x3, x4 circle. Therefore, tau is correct. Yeah, is labeling my world line. But of course, I could move it around.
And then phi, basically what? And second, whether your result is sensitive, whether you have another compact direction phi or no.
No, I mean, so what that does is, this instanton is going to have some collective coordinates, right, that correspond to the fact, that reflect the fact that I could rotate this configuration in physical space and place it in whatever orientation I want, and nothing would change.
Okay, although this particular choice coordinate may not have the same topology as the topology that you propose to analyze. Am I correct?
The topology would be the same.
Oh, even if we, okay.
If I'm just rotating things around?
No, yeah, but what you have in mind is if you add the asymptotic S1 cross R3, I think.
If I add,
Is that the question? You're asking?
You're telling me?
Yeah.
Oh, okay, sorry, I did. Okay.
You're asking what happens if you try to have S1 cross R3 at infinity.
Yeah, but that was simply S1 times S1.
Yes, crucially.
This is R4, it's at infinity.
At infinity, of course, is R4, yeah, which is important. I mean, I'm choosing to focus on field configurations where asymptotically things are flat. Okay, so this is just to say that, far away, you can check that regardless of what's happening at the location, like close to where this monopole is, this monopole world line is, far away, this looks precisely like one of the components of the familiar non-abelian instanton in SUN, okay? So, of course, an important, so I said earlier in response to Clay's question that whether something is a solution to the equations of motion or not doesn't preclude the fact that that thing will go into the path integral, but it is an important consideration that whatever field configuration I'm adding has finite action, okay? Otherwise its contribution will be suppressed and it will be effectively vanishing. So, of course, we cannot compute the Euclidean action for this particular configuration purely from the U1 gauge theory. Okay, I'm assuming that it will have to be sourced by some like magnetic and electric charges and so on. At best, I can make some guesses by assuming that there is some UV completion for the structure of this monopole, right? Purely within the U1 gauge theory, the action would formally be divergent. If I assume there is some UV theory that makes the singularity finite and there is some finite mass for the monopole, I can make an estimate for what this action would be, and you can convince yourself that it would be proportional at the leading order. The leading term would be proportional to the circumference of this world line, so 2 pi r, times whatever mass the monopole has. Okay, and there will be other subleading contributions. Obviously, to be within the regime where this effective theory describes my monopole, it better be that the size of this radius r is much smaller, in particular, that the scale set by 1 over the mass the monopole, right? At distances that are smaller than 1 over the monopole mass, then I'm really probing the structure of the monopole, and then I should really be talking about the UV theory. However, the action of this configuration wants to have a small r, right? This Euclidean action is smaller for tiny radius, which means that trying to quantitatively assess the importance of these field configurations is going to be beyond the U1 effective theory. So, of course, the most immediate thing you can do is see what happens when you turn these monopoles into Atouf-Polyakov monopoles, which we also discuss in this paper, and Marius will have a lot more to say on Wednesday. And what you can show is that the field configuration I've described in the context of the SU2 theory is really a smooth deformation of what we would call a non-abelian instanton in the spontaneously broken SU2 theory. So these types of instantons that have a small size are sometimes described or are sometimes referred to as constraint instantons, which are also not the solution to the classical equations of motion, but we know how to estimate their contribution to the path integral. And so what you find is that they contribute exactly just like you would expect instantons to contribute in terms of Euclidean action, which is a pi squared over g squared, except g squared now is evaluated in the UV at the scale of this Higgs bev. Okay, so in the non-abelian UV completion, these monopole field configurations that carry abelian instanton number are precisely, again, continuous deformations of the usual monopoles that we know exist in SUN. So what I'm going to turn to now, that is perhaps a little bit different and more interesting, is what if instead of going to the non-abelian theory, I try to UV complete, quote unquote, the structure of the monopole by turning it into a magnetically charged black hole. Okay. So as I said earlier, if I couple electromagnetism to gravity, it is possible to find configurations of this theory that do carry magnetic charge. Einstein-Maxwell theory is the lowest energy effective theory that describes our universe. If I integrate out all of the massive fields, quarks, leptons, including neutrinos, what I'm left with is Einstein-Maxwell theory with a bunch of higher dimensional operators. So since this theory necessarily contains magnetic monopoles, it also suggests that there should be field configurations that look like these types of abelian instantons that I was just describing.
And now you're in Minkowski space, well.
No, I'm actually...
Curved space, but the not Euclidean one, right?
Well, okay, I wrote this action here thinking about Lorentzian space, but just replace this with a plus, okay? Everything is true, and I'm gonna be in Euclidean space the entire time.
But what is written is Minkowski space.
I agree. But everything else that's going to follow is going to be in Euclidean. The solution exists both, of course, for Lorentzian and Euclidean, and I imagine for most people the Lorentzian discussion is more well known, but everything I'm going to say is going to be in Euclidean signature.
Familiar instantons exist only in Euclidean.
Of course. Absolutely. Okay, so how would this work out? So a quick reminder about the gravitational path integral. So again, in gravity, semi-classical gravity, we can try to study semi-classical gravity by considering our usual path integral, but now augmenting it to include also a sum over field configurations of the metric. Okay, and then ideally, in an ideal world, and of course, there are obviously some boundary conditions on the various fields that we introduce as part of our definition of the path integral. And so in an ideal world, there will be some subtle field configurations of this action that would allow us to write down the expression for the path integral in some form of semi-classical expansion on the right-hand side. The rules are, though, that we must sum over all field configurations, and once we include gravity, since the metric is dynamical, that should also include different topologies, okay? Subject to certain boundary conditions, which would include the asymptotic form of our space. Okay, so since I'm interested in connecting these to the path integral of our universe, I'm going to focus on solutions that are asymptotically flat. If I was very realistic, I would want them to be asymptotically de Sitter, but as you'll see later, that's not going to be very important. So again, I will be asking for asymptotic flatness. And so in the context of Maxwell-Einstein theory, to look for abelian instantons is to ask the question of whether there exist field configurations that ideally solve my Einstein-Maxwell's equations under the conditions that the metric is asymptotically flat, so there is not some weird topology just in the spacetime itself, and also that the electromagnetism carries some non-zero Check-Constraint number. Okay, so that's the question, and the answer is, turns out there is, and in fact, in some appropriate coordinates that I will want to spare you the details of, but let me just say a couple of things. So tau and phi here are the angles that I introduced earlier, and x and y are, x is some angular coordinate, and y is some radial coordinate that are related to my radial u and v coordinates from earlier. Okay, these are what's called toroidal coordinates. If you want to, look at that, and they are especially useful when you're dealing with situations where there are some localized, one-dimensional defects. So these coordinates are useful because the field strength of electromagnetism only has two non-zero components, and they are both constant. And they are proportional to what I'm going to call the magnetic charge of my black hole and what I'm going to call the Euclidean electric charge of my black hole. And it turns out this field strength is exactly the same field strength that exists in just the purely U1 for the abelian instanton. Okay, but it turns out that it is possible to find a metric accompanying this field strength that solves Einstein and Maxwell's equations, and the metric is of this form. Believe me when I say it's asymptotically flat, even though it's obviously hard to, you would never be able to, well, it's hard to see from this expression, but this is an asymptotically flat metric where this function gamma, which is the same function everywhere here, is some polynomial of the relevant variable, is a quartic polynomial, okay, that you can write in this form.
Sorry, before do you still have
yes.
a loop of monopole? So
yes.
So here, does it correspond to a ring singularity?
Yes.
Okay.
It corresponds exactly to the same type of, and I will show a little bit more what it actually means in this, with this non-trivial metric.
But it's smooth now, or it's still singular?
So because I'm doing everything in Euclid, you'll see it's a smooth, and because I'm doing, well, up to caveat, which I'll mention later, but this is Euclidean space. Unlike Lorentzian black holes, Euclidean black holes have neither an interior region nor a singularity, crucially. Okay, so in that sense, I got rid of the singularity at the center of the Dirac monopole. And there are also no curvature singularities in this metric.
I thought there were a new solution. You mean it's just the Euclidean version of a dionic black hole that you
No, it's not.
No. Right.
It's not.
So there is no.
Correct. So it is a new solution to some extent. So the C-metric, so this is what I'm calling the Euclidean dionic C-metric. The C-metric, which is just refers to this form of the metric, okay, where gamma is some polynomial, has been known for a long time, and there are versions of this C-metric without electromagnetism. So there's like the Schwarzschild C-metric, and there is also what people have studied in the literature is the purely magnetic C-metric. So people have studied this type of configurations when this guy is zero. However, obviously this guy is the entire reason why f wedge f is not zero, which is what we are focusing on. And that also changes some properties of the metric itself. So a quick comment. So one of the ways the C-metric has appeared in the literature previously, more interestingly, is, again, in the case where this is only magnetically charged. And the most famous version of it is that a version of this magnetic C-metric describes the decay of a homogeneous magnetic field into pairs of oppositely charged magnetic black holes. Okay, so if you think about, what would happen if you were in a lab and you were able to set up a homogeneous magnetic field as strong as you want, and your theory doesn't otherwise have any magnetic monopoles, eventually what will happen is that the magnetic field will decay into pairs of magnetically charged black holes. And this is a type of instability of a homogeneous magnetic field that was shown, I think, in the 80s or 90s by Gary Horowitz and Steve Giddings and collaborators. And the bounds that describes that instability is precisely a version of the symmetric where you only have magnetic charge. And you can show it has a negative mode, it satisfies all the features that you need for a bounce. So this is a slightly different version of that, where very importantly, we have what I'm going to call a Euclidean electric charge. And like the purely magnetic symmetric, this guy doesn't have a nice analytic continuation to Lorentzian signature. Okay, so an important thing for a Euclidean solution to be a bounce is that you have to be able to analytically continue it into a real valued field configuration in Minkowski's signature. This doesn't have a real valued analytic continuation, which is fine. Neither do SUN instantons. It just means it appears in the Euclidean path integral. It's a little bit harder to see, to ascribe some physical meaning to the process. So there are important differences between the two, but some iteration, the symmetric in various incarnations has been around for a while.
So this instanton, this solution should be some Euclidean space with extra, gauge field inside, right?
U1.
U1 field. And the question is, what is the topology of this Euclidean space?
Right.
Is it trivial or it's not?
It's not trivial. So maybe I'll show some images that will.
You will talk about that.
Yes. I'm not sure if to your satisfaction, but you can ask me more questions. So again, there are various parameters. So this looks a bit messy. There are various parameters, though, characterizing this solution. So the important ones are obviously the magnetic and this Euclidean electric charge of our configuration. There is some parameter R that, very roughly speaking, measures like the size of my black hole loop. And then in this polynomial, there are two other parameters, which are mu, that you can show that is related to the mass of the black hole, and then kappa is some combination of these various parameters that enters into what the geometry actually looks like. Okay. So crucially, as I said, if you take this and you compute just this, if you compute FHF, the important thing is that this will be not zero. These chi1 and chi2 are some functions of these various parameters that enter into this metric. If you demand that both the integral of f and the integral of FHF were quantized number, then this would just impose certain restrictions on the values that these electric and magnetic charges have to satisfy.
Okay. Why in this context again should we demand it? Now you're saying that it was a smooth manifold. So if it's a smooth manifold, doesn't it just come out to be whatever it comes out to be?
You have to quantize f such that it's a well-defined bundle over the smooth.
It's not a well-defined bundle. For this integer qm and qe there, that's not a well-defined bundle.
So it doesn't. So the integral of f by definition is just qm times. Well, it comes out to be qm times. Basically. Yeah, it comes down to be qm times whatever the gauge coupling, and then some parameter that depends on all of these various things. So it would only be quantized for certain choices, which I would say suggests that not all possible parameters will correspond to like legal field configurations that I should be summing over.
Like qm and qe are not the charge; they are just the parameter of your system.
There is some parameter, and then. Yeah, this is what it means to compute the charge, and that's what you want it to be quantized. In flat space, like all of these chi1, chi2s would just be zero, so everything would be like, the charge would be what you think is the charge. Like, it's just, I think it's something you have to impose at least at the level of this analysis. But yeah, happy to talk more about that.
So are chi1, chi2 one of those chi's appearing in the gamma of chi function or separate?
So chi1, chi2 are just some useful functions of these other parameters of the metric.
Okay, but then in the parameterization of f,
it turns out like if this is a quartic polynomial. One useful way of writing it is like I've done here, but another useful way is to write it in terms of the roots of the polynomial. So those are what these chi1 and chi2 are. They are roots, but you can re-express them in terms of mu and kappa if you want. They are just functions of mu and kappa.
okay.
So they are functions of whatever the mass of your black hole and the charges and all those various things.
But it's not the same high as in the formula well above, right? So there are
Yeah.
high 1 and high 2, and there is also high in the formula above. So that's a reason for confusion.
I guess my confusion
I'll
was
correct
that
that.
in the parameterization f, there is no chi appearing at all, and then you're computing topological object, and how would the metric dependence all of it show up in the f by f computation? I guess that
So this is coming about the fact that when you're integrating over important, good. So what you see here is that in flat space, these quantities x and y, these variables x and y, x, it's an angle, so it goes like from -1 to 1, and then y it goes from 1 to infinity. But notice, just by looking at this expression, for this thing to really represent a manifold at all, in particular a Riemannian manifold, it better be that the range of x has to be such that this term and this term are always positive. So gamma of x always has to be positive, right? But gamma of y always has to be negative. Otherwise, this thing is not even, R4 or like, Euclidean 4-dimensional manifold. So that in this curved space analysis, this restricts my range of coordinates to go no longer from -1 to 1, but instead from some chi1 to 1, which is why this is appearing here. And then similarly, when I do this integral over y, instead of going from 1 to infinity, I'm going from like 1 to chi2. And so that's why it's appearing there. Yeah. Okay, so let me try to explain what this metric looks like with some pictures. So first, let me look at what the Dirac monopole in flat space looks like. So again, I'm using here these u and v coordinates. So u is like the radial coordinate in the x1, x2 plane. V is the radial coordinate in the x3, x4 plane, which is where my monopole loop is. So for the Dirac monopole, this point here represents the monopole loop in the x3, x4 plane, right? You should think about the tau angle as going like out of the blackboard. Sort of, if you trace a circle like this, that would be tau going from 0 to 2 pi, which would be your monopole loop. So the monopole loop is this blue point, and then this orange line here is like the center, is like the interior of that disk. Okay, so that was the situation, the previous situation I discussed, the Dirac monopole. Now, when I turn on gravity, my solution, so this Einstein-Maxwell solution I was discussing, looks slightly different, right? So suddenly, a horizon has formed around the location where I previously had localized my monopole loop, okay, which is what this two-dimensional surface that I'm calling sigma h, okay? This is also, it's not really visible from the slides, but all of this stuff here and here is in gray, which is just a way of signal or put it in the picture that this is actually no longer forms parts of the space.
So it's a smooth boat or something?
It will be, yeah. It has to be checked that it's geodesically complete, so you have to impose geodesic completeness, but it is. So these regions here don't exist. So there is some region we have to excise because we've now got this horizon forming around the black hole. And then there's also something weird that happens with the geometry around what previously was the center of the disk. Okay, so there's some other special two-dimensional surface, which is this sigma disk surface. Okay.
And is it still R4 in the asymptotics?
Yes, always asymptotic R4, which is the really important part of this whole analysis, which is going to allow me to say that this type of field configurations should go into the path integral that describes our universe. So just to say a little bit more, so now we've excised the entire space in this region. That's what the metric I had previously represents. And I can convince you, hopefully with some pictures, that regardless of having excised this region of space, I still have what is a geodesically complete manifold. Okay, so now even though I'm using here UV coordinates, what I'm thinking is, this first quadrant is like some choices for my angles, tau and phi. This lower quadrant here will correspond to the same phi, but tau is like tau plus pi, and so on and so forth. So I'm just sort of like mirroring that quadrant like we do in electromagnetism. So what does this mean? So what I'm drawing here is, this space doesn't really exist. We've excised it. So what happens if I'm some observer that I'm traveling along some geodesics? It better be that I don't hit some kind of singularity, or that the space doesn't end within some finite proper time. So if I'm some guy that is like traveling along this geodesic here, and I hit this orange surface, so this orange surface is like the interior of this disk, this guy just continues traveling along the other side of the disk, which is here. Okay, just goes this way. Similarly, this other guy that hits the disk also continues on the other side of the disk. So in fact, what you learn is that this orange surface and this orange surface are identified with each other. Okay, so the interior of this disk is traversable, just like it was previously, even though gravity is scared, blah blah blah. But this is it's traversable just like it was before. However, if I'm some guy that is traveling along, say, this geodesic here, and I hit one of the black holes in my loop, what actually happens is that I emerge on the antipolar point of the loop, and then continue my geodesic trajectory. Okay, so this is why this particular field configuration, but also a feature of the other symmetrics that had been previously discussed in the literature, is also described as a Euclidean wormhole. Okay, precisely because of this feature. So, so one can check that this type of space is geodesically complete, and also you can check that all the possible curvature invariants in Einstein-Maxwell theory do not have singularities, so there are no curvature singularities. There is a subtlety, which is that there always are at least one conical singularity in the theory. So that conical singularity will be either at the location of this disk surface, when the magnetic charge is bigger than the electric charge, or on the horizon surface, when this is the other way around. And in some cases, it's both, when the two charges are the same, which happens both in the Schwarzschild limit, but also in self-dual configurations where the two charges are the same.
So does this mean that it's always present?
Always at least one, yeah. That's fine. The fact that there is some conical singularity just means that the equations of motion are failing at the location of the singularity. But again, it doesn't mean that I should not be including these into the path integral. What it does mean is that we are going to have to be a little bit more careful about how we estimate or how we calculate the contribution of these field configurations to the path integral. Okay, so fortunately, smart people have thought about this, and so the main idea is to rewrite our path integral into a sum over a different type of constraint action that is extremized by the configuration we want. And so this is in fact entirely standard procedure in non-abelian gauge theories, as was discussed in this paper, for instance, by Ian Affleck and also others. And then more recently, Jensen and also Patrick Draper have discussed this in the context of the CITER, and also looking at the various forms of Euclidean black holes. Okay, so schematically, the idea is that I have my path integral, okay, here in Einstein-Maxwell theory that I define in some appropriate way. I'm going to introduce some delta function. I'm going to introduce some new variable sigma, okay, that I'm integrating over. So I'm integrating over sigma. But I'm also including this delta function that enforces sigma equals some functional of my fields. So effectively, I'm doing nothing, okay, by doing this, by introducing this new variable with this delta function. And here, I'm just writing down some general functional of the relevant fields. In this example, it only has to be a functional of the metric, so I'm simplifying it to the case, but it could be a more complicated thing. And then as a second step, let me rewrite this delta function by using its Fourier expression. So by introducing yet another variable, this lambda, and writing this delta function as an integral over lambda of this complex exponential. Okay, the standard way we use to represent delta functions. And so now the idea is that I've conveniently turned my original path integral into something where it looks like I'm doing a path integral over a slightly different action that I'm going to call the constraint action. Okay? So now the idea is that, well, maybe I didn't know what are the saddles of this action, but if I know the saddles of this action, then maybe I get to do my semi-classical expansion and expand the integral over G and A, and then do the integral over sigma effectively at the end. Okay? So this allows me to obtain some kind of effective expression for my path integral, where with the caveat that what I have left over is some leftover integral over this variable sigma that I introduced, that at the end of this whole process appears as if it would be an additional collective coordinate. Okay, so just to remind you, in non-abelian gauge theories, when I have a Higgs, I no longer have classical field configurations. My instantons are no longer classical field configurations that solve the equations of motion. So what we do there, what this paper does, is introduces a constraint that constrains the size of the monopole to be something fixed. But then at the end of the calculation, what we end up with is an integral over all of those possible sizes. Okay? And so you can do similar things for black holes or for the Citrus space. The sort of non-trivial part of all of it is to find what are the functionals that you have to choose to get the appropriate constraint action. And so we show that in this particular case, these constraint functionals are proportional to the proper areas of this disk and of these horizon surfaces. Okay. So after I only have 2 more slides before the conclusions. So in the end, when all of that is done and dusted, you can show that the contribution of this type of field configurations to the path integral end up looking something like this. Okay. So there are lots of things here. Most importantly, this exponential suppression, so here SE really refers to the Euclidean action of the symmetric, to the field configuration that I've been describing, which we can compute, and I will show in a second what it looks like. Here in front, there are some, you could also compute the one loop functional determinant, so this could be out here. Here, this is an integral over both the proper areas of the disk and of these horizon surfaces. So as I advertise, we are left over with these integrals after imposing these constraints. J here is like some Jacobian determinant that in general will be around. There is also, as usual, some integral over collective coordinates. So in this case, I can move my instanton around, right? Translations are collective coordinates. This is a loop, so I can also do rotations, and that's also a collective coordinate. So yeah, that's just what I mean by this. And then, of course, I should also be summing over all of the various values of my 2 integers that are characterizing my integrals over f and f wedge f. Okay, so I will be summing over the different topological sectors as well. So importantly, unlike what you would find for a Dirac instanton, where the action of this field configuration is formally infinite because there is an actual singularity, this Euclidean action at least is finite, and if you were to compute it, you will find that it looks something like this. So this first term here comes from the Maxwell piece. Again, chi2 is some function of the various variables that define my field configuration. Notice the 2 pi squared over e squared out front, which is the main feature. And then this piece here comes from the Einstein-Hilbert piece of the action. And so notice this is the geometric mean of the proper area of the horizon times the disk surface. Okay. So in general, this looks like some mess. It's interesting, I would say, that this Maxwell piece is the smallest when, this is not obvious from this equation, but for configurations that are self-dual, where this Euclidean electric charge and the magnetic charge are the same, the minimal value of this Maxwell piece is precisely 4 pi squared over E squared, okay, which is very, instanton-like, obviously. And then we have this piece from, the Einstein-Hilbert part.
I guess is n squared over n squared.
So n is, if you want, the integer that I was using to write down the integral of f with f.
Ah, sorry.
Yeah, little n, and then capital N is like the magnetic charge. Yeah. So.
This answer is sensitive to the fact that you have the conical singularities. Like if we put a bunch of tower.
So I'm already including that fact.
But if we had put a tower of higher derivative operators, could we have, in principle, computed sufficiently many derivatives of the curvature to sample those singularities?
So I don't think so, because these are not curvature singularities. I think these are conical singularities, and I can completely account the effect of this.
Singularity is not a curvature singularity. Some localized.
There is no curvature invariant. It's slightly different. And it really just signals the fact that my equations of motions are not satisfied at that point. And I think, but the constraint instanton method does allow you to include the effect of those. It is absolutely the case that this is, we've only done this at the level of Einstein-Maxwell theory, so there are only 4-dimensional operators here. Yeah. So if you do this more generally, and there is, other stuff going on, it could change some of this, but I don't think the conical singularities will be the reason why. One thing that is important, though, is that what you see from here is that it's good news. This is finite, unlike for the Dirac monopole. Obviously, this Einstein-Hilbert part prefers small things. In particular, it prefers a small area of the disk, but it also prefers small horizons. Of course, we know that for us to have a good semi-classical gravitational expansion, all distances better be bigger than the Planck scale. So this does suggest that getting a true quantitative answer is sensitive to whatever UV completion of quantum gravity we have. Of course, what to some people is a sensitivity to quantum gravity, to others is a potential window into the UV. I would say that the fact that this is nevertheless finite and also not small, so this leading term here is already large because E is perturbative. It's interesting, and one can check. So the fact that the action is finite, there's a question of how big or large it is depending on what quantum gravity is doing. But this allows us to see how theta, in particular electromagnetic theta, enters into physical observables, right? So in particular, there will be a theta-dependent contribution to the vacuum energy density that we can estimate in the usual way. So here I'm only including the leading contribution from the instanton 1 sector, and so. Yeah, so this d for x, this is just the integral over collective coordinates, and what we learn is that there will be some contribution to the vacuum energy density that parametrically, the scale has to be set by M. Planck in some way. This exponential suppression will be inherited from the expression that I had in my previous slide, and then this cos theta appears by doing the sum over the various topological sectors, n1 and -1. And similarly, other operators. So this is, for instance, the expectation value of E dot B, and I really mean Lorentzian E dot B. This will be proportional to some, now the path integral, but I'm inserting here f with f, Euclidean, but this is why this I appears here. And so this also comes out to be, something real, not zero. In this case, proportional to the sine of theta, just like what happens in QCD. So in particular, looking at this last expression here, what we can think of is that, so this suggests that this Euclidean wormhole is really capturing the effect of quantum fluctuations that involve the pair production and reannihilation of oppositely charged, magnetically charged black holes. Okay.
Can I ask? So if you compute like in a small gauge instantons for non-Abelian theories, you typically include also the effect of light charge fermions.
Great.
So should be.
You should, because there are fermions. So let me actually, it's one of the things I have in my conclusions. Yeah, so first of all, I would say the electromagnetic theta term is a physical parameter of our universe, and we don't have to produce a monopole or find a monopole and then measure its various energy levels and charges in order to measure that theta, okay, at least in principle. There will be leftovers of that theta at low energies. So I mentioned the contribution to the vacuum energy density or some expectation values of some Lorentzian operators that will be proportional to theta. Most interestingly, something that will also should be proportional to theta is the electric dipole moments of any elementary fermions that are charged under electromagnetism, right? But in order to calculate that, and also the effects of theta more generally, as we're used to, we have to see what this type of field configuration looks like in the presence of fermions, and whether there exists zero modes in the background of this instanton. And so I suspect the answer is yes, but it's also a little bit messy, and it's something we've been thinking about. But I think understanding the effects of fermions, actually not just obviously in the gravity case, but also even just in the U1 Dirac monopole case, is something that is important. It will mean whether all of these physical effects of theta are suppressed by some power of the Yukawas, right? There'll still be not zero, but could be even smaller. So also I would say that this electromagnetic theta term is ultimately a window into the UV. Okay, it could be either the grand unified theory that unifies the standard model. If these instantons or monopoles are this type of non-Abelian fields, or maybe even something more stringy or like quantum gravity related. So, and we do have a lot of constraints, experimental constraints on things like the electron EDM, or things that in principle do depend on this electromagnetic theta term, okay? But we don't really know quite how all of these contributions actually show up in the prediction for those observables. So I think more practically, I think it would be very helpful to find examples where these calculations are under control, meaning some configurations where this type of instantons are actual saddles. So that could be perhaps in the context of extra dimensions or finite temperature, stuff like that, and see what repeat this calculation in that context where you don't have to impose some constraints. And just more generally, I would say there are many interesting aspects of theta terms and their phenomenology still to discuss and to discover. And I would just mention also a month after our first paper, Alexei Sherman and collaborators had a paper where they also mentioned, they also discovered the sort of Dirac field configurations that carry instanton number, and they discuss also some other interesting theta terms beyond what we normally think of theta terms. So that's just an example of that statement. So thank you. Yes.
So you said that your solution, asymptotically they are R4, right?
Yes.
But there are proper gravity instantons which are not R4, like Abelian, things like that. And the question is, what might happen if you couple that to U1 field?
Sorry, so there are other gravitational instantons where the space asymptotically is not R4?
Well, of course, Euclidean instanton, well, it's locally R4, but globally it's not R4. It's
so her point was to do R4. Actually.
Huh?
Her whole point was to do R4.
Asymptotically R4. So the geometry far away is R4?
That's exactly the question. So you can consider also, manifolds with other topologies.
Yes.
And couple them with the electromagnetic field. And it's also some question which might be posed, right?
Sure, but I would say that, if I want to compute the Euclidean, the path integral that is appropriate to describe our universe, and I think that our universe is asymptotically flat.
Path integral is something complicated, right?
Sure.
Gravity. So you are.
But we do impose certain boundary conditions on the things we sum over, and one of those I think is the asymptotic behavior of our fields, the metric in particular.
And also, for example, even if you have Minkowski flat space, then the Seguchi-Armstrong instantons may be considered as a tunneling transition when the space is transformed inside R, something like that. So these Euclidean configurations, they needn't be R4. So it's just a question, you didn't do that, but probably it's interesting also to do that.
I agree. I think it's really interesting to think about, what other types of field configurations enter into the path integral that would make, for instance, this theta term physical. Maybe they are more important than what I've described here.
One can study first classical configurations and then think about path integrals, right?
Sure. Yes.
So I wanted to ask you if your singularity, you can make them such that they are actually orbifold. If you can have.
You're talking about the conical singularity?
Yeah, if the conical singularity can be a discrete number multiplying the.
Multiplying what?
So the defect angle can be irrational, but it can be sometimes such that you just have a multiple number, so you can understand this as a discrete orbifold, which is nicer because this is the type of geometry that you can then split into smooth geometries.
Okay, I have not thought about it.
So you did not?
No. Yeah, there are some versions of this where, the only examples I know of how to remove the singularity. So for instance, in the magnetic symmetric, or when the magnetic charge is larger than the electric charge, then you only have one conical singularity, which is localized in this disk. And so one version of the symmetric that doesn't have this conical singularity is the version that describes the decay of this magnetic field. So the way it kind of solves the singularity is that, that is not flat space. It's not asymptotically flat space. Instead, you have a magnetic field that extends all the way out to infinity. So it is, what people call like this Melvin universe. So it's sort of like some magnetic field that effectively is localized in this region. And itself, it looks like from far away, it looks like a cosmic string with the opposite angle axis as your conical singularity. And so that cures the conical singularity that you had on your disk, but it comes at the cost of something that is no longer asymptotically flat. So that's kind of the only physical example I know of situations where some of these conical singularities are gone, but I haven't thought about it more than that. Yeah. Here we were just happy with the fact that there is some way in which we can at least estimate the contribution to the path integral and see that that is finite.
What I have in mind is more like a Gibbon-Soking monopole instanton where you would have a pole which is not 1 but 2, 3, 4, and you can split it into several. So here you may have a singularity which is just due to the S1 cross S1 symmetry that you could imagine is resolved.
I see.
If it could be a multiple integral.
Okay. Yeah. Happy to discuss more.
So is there any point in building QFT models that have like a high quality axiom?
Well, there is, because I think there is in general. Definitely, the answer should not be no because of this. Because I said you can. Is this UV sensitive? Blah blah blah. Quantum gravity, but there is already this piece here, right, coming from the Maxwell term, where E is the E of electromagnetism. There's a 4π² here. This is already like 100. So this is already suppressed by to the minus 100, which is a small. Even if it goes into the action potential, it's still a very suppressed. Of course, in situations where you have large extra dimensions and maybe some, this is played by the role of some other type of monopole that is not just GR all the way up to the Planck scale, which is what I'm assuming here. That could be stronger, but certainly not in the minimal. Black hole loops spoil your axion shift symmetry. That's small.
Can I have a question or comment about big picture level, what has been achieved here? So I have therefore two questions. One on the pure QFT context, the first part of it, and the second with the gravity.
Right.
So in the QFT part, I think it's hard to talk about the abelian theta without talking about UV completion, because otherwise you get basically zero effect all the way through. So in order to talk about any finite effect in your physics, you have to make you have to think about dynamical monopole. Therefore, it's necessary that you talk about the proper UV completion that allow you to talk about turning on F with J.
Sure. So in our paper, the second part of our paper really focuses on the non-abelian UV completion that Marius will also talk more about on Wednesday, and what that looks like if the monopole was like a tooth Polyakov or something else.
Good. So what I'm trying to do here is that starting from the U1, and here's a data parameter.
Right.
I know two ways of turning on f wedge f. One is having a UV embedding, and that there's a a suitable UV structure allow me to turn on the f wedge f in the IR. So that's first scenario. Second one, let's talk about gravity case. Is your achievement because I didn't have all the technical details. It's a great piece of work. I just sounded like a Trump biker. I'm very sorry about that. So is the achievement you had, or one of the achievements you had, equivalent to turning on f wedge f with help of a gravitational configuration that prepares a proper topology for you?
Correct.
Okay, so these were the logical two ways.
And so this is not a choice you have, right? Like
okay,
the metric is gravity is dynamical. There will be quantum fluctuations of the metric. Some of them will have non-zero topology, and what we've shown is that some of those will also have non-zero f wedge f.
Okay, great, thanks.
And I would say that, I mean, of course, anything where you assume this is just like minimal coupled to GR, the answer is going to be really tiny. But I think it raises the question that whatever string theory we have or extra dimensions we have, as low energies, it better look like Einstein-Maxwell, right? And then I think there is an interesting opportunity to say, this could be, indeed, it's going to be very tiny if this is just GR all the way up to the Planck scale. But when we measure things very precisely that are potentially sensitive to theta electromagnetism, what are we learning about the UV? Okay, right. So there could be other situations where you can do this calculation and the answer is a lot bigger. And so are these constraints are they telling us something interesting, putting interesting constraints in some non-abelian theories or like some stringy, implementations and so on.
Okay, great, thanks.
Okay. I think we have a lot of questions.
Sure.
Thank you.
Thank you.